Very welcome back to our channel. And today we have brought to you another topic, and this time it is a very special topic called as phase lock loop. So, in short form, we would call it a PLL, and this circuit or this electronic system is widely used in several of applications. So first application we would say in digital system design containing microprocessors and microcontrollers, you need a reference clock and you have a clock that is fed to multiple of the digital logic inside a digital system, and there is a synchronization therefore in between the clock signals. So PLL is used for that purpose. Second application, it is also used as a clock multiplier. Let's say you generate a reference clock of 1 megahertz and you need 100 kilohertz clock, you need 10 kilohertz clock to be fed to the other digital blocks into your system. So you can basically also call it as a clock multiplier or a clock divider. So you generate a 1 megahertz clock and then you divide it to in such a way that you get the 100 kilohertz, 1 kilohertz, and so far and so forth. So PLL will be used as we will see how it divides that clock signal to be used as a clock divider or clock multiplier. It is also used to demodulate your signal. In radio communication, you have frequency modulated signal that is transmitted by a transmitter, and at the receiver end you want to extract the original FM signal. So in the demodulator block you can use the PLL to extract your original FM signal. Then there is this local oscillator. As we will see now, the local oscillator also can be implemented using PLL method. Finally, PLL also forms an important block as a frequency synthesizer in vector network analyzer. So you have this instrument and in that you have got this frequency synthesizer, and PLL is a primary block in implementing frequency synthesizer. So basically, we are going to see what exactly is PLL by understanding its fundamental principle of operation. So as you can see that phase locked loop, as the name suggests, it is a loop. The system has a loop. It means it is a closed loop system. We are going to see whether it uses a feedback, which is positive or negative, because we are talking about loop. So it is a closed loop. It means there is a feedback. And if there is a feedback, we want to understand whether that is a negative feedback or a positive feedback. So we'll see that in a moment. Next question, you can see that it consists of primarily three blocks at the most fundamental level. First called as phase detector or phase comparator. Second block is a filter, and third block is a VCO, that stands for voltage controlled oscillator. It is called loop filter because that is placed in the feedback loop of the PLL. So you have got an externally applied input signal VI, and you have got the output of this signal of the system VO, which is also fed back to be mixed with the input signal VI. So this is your feedback right here. Okay. So now the definition of the PLL is that it compares the phase of a reference signal VI to the phase of an feedback signal VO, which is also adjustable. I repeat again. So it will compare the VI signal right here. It has got frequency and the phase. For example, it is a sinusoidal signal. So it has got frequency and the phase. And the output signal is also your sinusoidal signal, which has got frequency and the phase. So the job of the PLL is to compare the phase of the reference with that of the feedback signal. And accordingly, make sure the feedback of this output signal is matching to the phase of the output signal is in match with the phase of the input signal. That's why we call it as a phase lock loop. And when that condition happens, we call it as a phase lock loop. Okay. So we understand this with this basic waveform. Consider you have got the reference signal, which is indicated by the red waveform, which is a sinusoidal signal. It has got the amplitude A right here, and it has got the phase starting from, well, let's say you got the phase of the signal is 0, Here you have got the phase of the signal is 180 degree. Here you got the phase of the signal is 360 degree. So that is the phase expressed in degree. You can also express the phase in radians. For example, here is you have 0 rad per second. Here you have pi rad per second. And here the phase at this point, you have the phase of a signal of a red waveform 2 pi and expressed in rad per second. So that is how you express the phase. Now we call it as the input signal Vi, and let us say this is your reference signal or the feedback signal, which is also an output of the PLL, which is called as VO or the V reference. So you've got this blue line where you see that the phase right here is 0, and let's say phase right here is pi, and the phase right here is 2 pi. However, with reference to the red signal, there is a clearly a phase shift, as you can see that. So in degree, you can see that we say that there is a phase difference between the two. That is this point, and that phase difference is theta. So the job of the PLL is to maintain this phase difference, whether it is 0 degree or a finite value. Let's say, for example, theta here is equal to 45 degree, or let's say pi by 3 rad per second. So whatever the phase difference, if any, between the input and the reference is there, job of the PLL is to lock to that and hook to that and maintain that all throughout the operation. Then only we can say that the phase lock loop is working properly. So I say again, if there is a phase difference between the two signal theta, which can be 0 degree, and theta can be a finite value, for example 45, 553, whatever the value. So job of the PLL is to be locked and remain locked at this phase difference. If the phase difference is 0, it will make sure always the phase difference will 0 between the two signal. And if the phase difference has a finite value, in case in this picture theta, it will remain so. So for the phase difference of 0, along with the red signal, the output signal or the feedback signal will also have this kind of waveform. And in the case you have a blue signal and you want to maintain this phase difference of theta, then PLL can also work in that fashion. Okay, so what is the hardware available to implement used as a PLL? So here is this IC that is HC4046A. You can type this number on Google, get the access of the data sheet from the manufacturer, and you can read the data sheet about all the information relevant to that. Second IC available in the market is the CMOS. CMOS, complementary metal oxide semiconductor technology, and the IC name is 4046. You can again type the name of this IC in the Google and get the access to the manufacturer's datasheet. So it is basically a digital PLL, which can be implemented using CMOS technology. So you can see that it is a 16-pin IC, and you've got the total pins 16, and each pin is described right here as shown in the figure. Now we want to move to the next slide. So when we say the phase PLL is locked, as I said in the previous slide, when we want to say the PLL is locked, it means we want to say that it is working properly. And when we say that PLL is locked, it means in a steady state, the output frequency, let's say you have got the signal here, and the frequency of the output and the phase of the output are in perfect match with the frequency and the phase of this input, which is the reference. And this is when this happens, we say that the PLL is locked. And when it is locked, the two signals, that is Vi and the VO, will have exactly the same frequency, and their phase difference will either be 0 or there'll be a constant finite value between the them, which will be maintained throughout. So PLLs, they can have output frequency ranging from a fraction of hertz. Let's say even you can have a 0.2 hertz, something like that. And you can go in designing up to many gigahertz. So that's the power you can have that. So let us move to the next slide where we are going to see three stages of the PLL operation. So when the PLL is designed like this and using this hardware, you say that initially before the lock, we turn on the power supply and we say that the circuit or the system is in the free running condition. It means the center frequency of the PLL, which is decided by this voltage control oscillator, which is also a local oscillator, the frequency of this VCO will run when not locked to the input frequency. So let's say the frequency of the input signal is F and the frequency of VCO will be F plus minus Fi. Okay, so where Fi is some difference between the output frequency and the input frequency. So the VCO is running at its local frequency and the circuit is not locked to the frequency of the input signal. Then the second stage is called as capture. The first stage is free running. Second stage is called as capture. So in order here in this stage, in order for the VCO to get locked to the input frequency initially, the frequency of the VCO must be within the PLL's capture range. So that is called as PLL capture range. So capture range would be from this point to this point. So when you design a VCO and you know what is going to be the reference input frequency, accordingly you design the VCO frequency, and then little bit deviation from this point to this point will get adjusted so that VCO frequency will get locked to the input frequency. And the third stage is called as phase lock, or it's called as tracking stage. It means once the VCO signal frequency is locked to the input frequency, the PLL will continue to track and adjust to the input frequency as long as the input frequency is within the capture range of the PLL. And the PLL's lock range is wider than the capture range. This is the third point you want to mention. So there are two things to be named. One is called as capture range. Okay. PLL's capture range, and the second point is PLL's lock range. So these two important points you need to understand. Now we move to the next point where we can see that the PLL is basically a control system. So what is mean by that? It means the VCO frequency will be continually adjusted by the input applied to the VCO so that this VCO's frequency signal will always be in lock. VCO's output signal will always be in phase lock with the input signal applied to the phase detector. Okay, so when we say that keeping the input and output phase in lockstep, it also means keeping the input and output frequencies in the same, to be same. Again, I repeat again, when you successfully manage to lock to the phase of the VCO signal to the phase of the input signal, you also manage to lock to the frequency of the input signal. Okay. Now, there is one more stage. As I said in the beginning of the slide, we can use the PLL to be used as a clock multiplier or clock divider. So basically, let's say I want to use multiple clock frequencies. So what I will do, let's say the input reference frequency signal is 100 megahertz. And now I want a 1 megahertz signal at the output. So what I will do, I will place divide by n circuit here, which is usually implemented by the digital logic, such as here you see the n-bit counter. Here the n-bit counter is used, which is the digital logic. So you've got the input signal frequency to be 100 mega, and the output I want only 1 mega. So I will use divide by 10 counter here. So 100 megahertz divide by 10 will be giving me the I will use the divide by 100 counter actually, so that I will have the 1 megahertz frequency right here. Okay, so by incorporating the frequency divider block, the PLL can generate the stable frequency at the output, that is multiple of the input frequencies. So you can say that. Okay. Now we want to see what comes the next. So just to summarize, we see that the oscillator right here is generating the periodic signal V naught with a frequency proportional to the applied voltage. So right here we have the oscillator, and that is generating the reference signal VO, which is controlled, the frequency of which will be controlled by the input applied to the VCO. That's why it is called as voltage control oscillator, because the oscillator's output frequency is controlled by the voltage applied at its input. Now, what is the phase detector doing here, or the phase comparator? So it basically compares the phase of two signals, the phase of the input signal and the phase of the feedback signal right here. So you can see that I am drawing this signal in this way, and I'm drawing the feedback signal right here in this way. So in they are in phase difference to each other. So the feedback signal is out of phase with the input signal, and that is why it is called as negative feedback. If the feedback is in such a way that the input signal and the feedback signal both are in phase to each other, then you can say that that's a positive feedback. Okay. The phase detector is going to compare the phase of the VCO's output along with the phase of the input signal, which is a periodic reference signal, and it outputs a voltage right here, which is becoming an input to the loop filter, and this voltage is getting stabilized by the loop filter and coming right here to control the frequency of the VCO. Okay, so that this output filtered by the low pass filter comes here, and it helps to adjust the oscillator frequency to match to the phase of the input signal with the phase of the output signal. So idea here is to the lock to the same frequency, so that frequency of VI is equal to frequency of VO. It is a negative feedback system, and using a frequency divider is option if you want multiple of the signal frequencies. So we can assume that initially the oscillator right here is nearly at the same frequency as the reference signal. So if let's say the frequency of the input signal is F, we can also assume the frequency of the output signal is also F. Okay, which is usually not the case, but for the simplification, we will assume that the frequency are nearly equal, approximately equal, or we say that FVI is approximately equal to FVO right over here. So if the phase from the oscillator, if let's say the FVO right here becomes less than FVI, okay, then the phase detector's job is to change this control voltage in such a way that the oscillator's frequency gets increased. And so that again, FVO will become then not approximately, this time it will become equal to the input frequency. For the opposite step, if FVO is greater than FVI, then again the control voltage will be adjusted so that FVO will become again FVI. So that is how the things will happen. Okay. So with that said, let's understand what is locking range right here. So locking range, we have seen that once you got the phase lock loop working properly, but there is a case that initially your oscillator is far from the reference frequency. Let's say the FVO is much greater than FVI, or FVO is much less than FVI. So the oscillator's reference frequency is far from the input reference frequency. So then your phase detector or phase comparator, they may respond to the frequency differences so as to increase the lock-in range of the allowable inputs. So basically, you design this phase comparator in such a way that they should respond to the large difference between the frequency of input VI and the feedback signal VO. Okay. So let us understand how they do it. The phase detector, they generate a voltage which represents right here the phase difference between VI and the VO. And then that PD output that is the phase detector output, is used to control the VCO right here. Of course, stabilized, that output is stabilized by the loop filter. And then the phase difference between VI and the VO right here is held constant when you have the controlled frequency of the oscillator, making it a negative feedback system. So phase detector can be implemented by a simple block diagram, a simple circuit called as frequency mixer. So you've got the input signal VI right here, and you've got the local oscillator, that is VCO, something like that. And you have this ideal multiplexer, which is basically a multiplier. And then it generates the output signal, which is the output right here. Okay. But that drawback of the using such a simple frequency mixer as the phase detector is that it generates the spurious sideband. So the output signal of this mixer would be a carrier along with the two sidebands, but it will also have multiple sidebands near the carrier. So they are called as spurious or unwanted sidebands. Okay. And using this frequency mixer as a PD can also reduce the capture range well below the requirement, and it can also increase the lock time beyond the requirement. So that is the drawback. So what to do? So solution is to use the digital phase detector. So instead of frequency mixture, which is the analog form of PD, why not use the digital, for example, as simple exclusive OR gate, which symbol of this is shown right here. So the advantage of using digital version of PD is that they don't produce spurious component at their output. And when they are used as a PD and the PLL gets locked, the steady state phase difference at the input using the XOR gate is 90 degree, nearly 90 degrees. So always this phase difference phi or theta will be 90 degree. Okay. So in PLL application, you often need to know when you design PLL, you often need to know whether your PLL is in lock mode or it has come out of the lock. So XOR gate can help in doing that. There are more complex digital phase detector available. They can be used and they produce the output that allows the reliable indication whether your PLL is out of lock or not. Okay. Now let's have few more points about what filter does. So this loop filter, which is basically a low pass filter, its primarily job is to maintain the loop stability. It also determines locking time. It also determines lock-in range. So when you design the loop filter, you need to consider these 3 points: loop stability, lock-in time, and lock-in range. It also helps when the phase detector produces the output, it can have ripples in the output. So the job of the loop filter is to limit the ripples. It is just like acting, that's why it's called as filter. There are design trade-offs, however, for the loop filter. It increases the bandwidth. If you want to larger bandwidth of this filter, it will decrease the system stability. Too much damping for better stability then will also reduce the speed and increase the settling time of your system. So final implementation or final little bit advancement of the PLL is that use a frequency synthesizer. So what you do basically, if you have a look carefully between the basic block diagram that is right now shown here, it has 3 blocks, and for the advanced one, that is the frequency synthesizer right here, you have got the phase detector as in the basic one, you've got the low pass filter, and you've got the VCO. So internals of the VCO is also shown right here. That is bias generator, VCO, and output converter. That makes the VCO. And additional block here is charge pump. And then you've got the input reference coming FI, and you've got the output signal, which is also the feedback to the input through this optional divide by n circuit. And this is the output signal. So this is your frequency synthesizer circuit. So This frequency synthesizer basically helps to produce range of frequencies from the single frequency available at the input. Okay. So this kind of frequency synthesizer is used in vector network analyzer. They are also used in computer clock generation. And in the PLL, the divide by end circuit is used in the feedback path. Okay. So hope you found this information about what PLL is, how it works, its different block diagrams, working principles of each of them, understanding definition about what is phase lock loop, what is lock range, what is clock range, understanding the three stages of operation such as pre-running, capture, and lock and tracking. So all this information we gave by researching resources from various sources from the industry, higher education industry and all that. And we compiled that in this particular module that we presented to you today. Hope you found this video useful. And if you did so, click the like button, share this with others for wider reach, and stay tuned for more engaging content like this. Till then, wish you a very happy learning.